Oh, yeah, hi. Good evening, everyone. We'll wait for some time. Let the others join, then we can start again. Shall we start? Uh, we'll wait for 2 more minutes. If anyone have any doubts, please you can ask. The- I think that we can start the session, is it? Or we'll wait for some more time. Yes, good evening to everyone. And my name is MD Sidraja. I'm PMRF scholar in Tiruchirappalli, and I'm doing that my PhD in the field of that biomechanics and all, and that machine learning. So Today we are going to today we are on the fourth week of the course on the machine learning for engineering science and application. And till now we have started like we have started to make the grounds and all. And today we will be jumping into the basics of the machine learning, like linear regression and all that, how the things will go and all. Before jumping into that exact like deep learning or maybe deep learning or that CNN or ANN or even with the supervised learning or maybe that auto encoders and all. So today we'll see like how the things will go and all. So can anyone tell like how what if I'm saying the machine learning is something that what do you mean by what do you mean of that machine learning? Or even just believe about the machine learning, what do you mean by that something called learning? And anyone tell like if I'm saying something that learning, what does it stands?
Learning means
Learning from
we
data.
identify from the data pattern insights.
Yeah, like learning is something that we are going to learn from the past experience or something that we are trying to something to train the things and all. So learning like is something from the past experience and all. So it's the same way that if any machines and all, they have some past experience or that we are going to train from the data and all. So it will terms as a machine learning. If we talk in that layman language, so we'll say that any of the kids they're going to start in the play school and all. So they're learning. How they're learning, like with the help of the data or maybe that pictorial presentation or that the parent itself they're going to show or will tell this is this and all that will tell. So that's how they're going to learn. Like it's something that will comes with the experience. So this is how the same thing we're going to start in that also. So we'll talk bit of brief like what we have discussed as such. So I'll tell like how it went till now. Like we started with the what do you mean by machine learning? That introduction that gave that, and then we gave that agenda of the full course and all. So before it's jumping into the directly to the machine learning and all, or we'll go directly to the our here structure itself. So if you see here how it went, like we started with the how introduction to machine learning, then we have talked about a bit of algebra. Because once we talk about, I have told like when we are going to deal with the machine learning, so it's a more or less a problem of the optimization. Optimization is nothing. It's a numerical methods we can say, or the maths itself we can say. It's something that we have to do the optimize. Either we have to get the maximum value, or maybe that minimize. So in the terms of machine learning, we'll not talk about the maximum and all. We'll not go for that. Just 1 minute. So we'll not talk much of about maximus like maximum and all. We'll say like we're going to convert the maximum into the minimum. Let's say I have to get the maximum accuracy or something that is the maximum, but we're going to reduce the error or the variances and all. So it's a minimization problems will be there. So it's a full of like optimization problem. Like then we have discussed about the probability. Probability like we have to define the threshold or what will be the standard deviations, expectation, or maybe that bias and all. So that's all we have discussed about. And then we were having that Bayes theorem because when we're going to find out something, so we'll be having a conditional that one probability will be there. It's something that happened already. So how the machines they're going to learn from there also. So it's something called conditional probability, and all will be there. So that the one that we have seen bit of brief of that only. Apart from that linear algebra and the probability that we have a statistical that methods will be there, statistic course will be there. That's also be very useful. That's a very useful for that parameter significance and all. But in this course, that might be not that much useful. But when we go full fledged in the biomedical applications or maybe the clinical health and all, so it will be very useful because before going to train for any model, we have to give some input. That input can go in any form, maybe that in the form of the image or in the form of the signal or in the form that we have to put some labels and all. So before giving into the that models and all. Okay, so before like we are going to jump into giving that feeding data to the model, whether it's making significances are there or not, or maybe the data that all the features have the significant differences are there or not, or either it going to create the noise, or maybe that unnecessary that either the overfitting can happen, maybe the variance will be the more, or maybe that underfitting can happen. So so before that we have to check with the whether the features we have taken out, whether they are having the significant differences are there or not. Like it's something called t-test or PRT test, ANOVA will be there and all will there. So that will be there. So once you will go into that application problem, that will be going to be that will be going to be a that beneficials and all. But here we are going to making the foundations of the machine learning. So we'll talk about the more of the algorithm. We'll talk more about the models and all. So we'll not go much into the parameters or the data itself. Okay, so then after we came across that one optimization problem, like optimization, like how the things will go and all. In that a constant optimization, like when will we having for a certain that limit for that particular limit, what will be the optimization that optimized value. Then we were having unconstant optimization for a that is a real number, like from the minus infinity to plus infinity. That what is the optimum value will be there. So there are two types of the constant was there. Then we were having like optimization problem was there. Then we have discussed like how we got the optimum value based upon the like if it is the scalar, then we were doing simply that first derivative then according to the zero. So when we were having simple when we were having simple like when we were having simple just one minute. When we were having simple scalar problem, so what we'll do, we'll take a function will be there, so that we are going to take first derivative and we'll equate to zero. Then to get the nature, either it's a local maxima or the local minima. So that for that we have to. Is it audible? Can you check? So, yeah.
Sir, it's
Yes, yes,
audible.
audible.
Audible, sir.
Thank you. So I'm just giving a brief, like in last 3 weeks, what we have done. So we have checked with the whenever we were having the scalar. So we were just going with the first derivative to get the optimum value. So now we have to check with the whether that value is that's going to be a local minima or the local maxima or saddle point and all. So to get so then we were doing the second derivative. Then if it is value is going to be negative, so we'll sell the maxima. If it is positive, so we'll say minimum. If it is equal to zero, then we'll say that it's a saddle point or critical point. That's how we're going to tell. So, but in the machine learning, we don't have the scalar problems, even though that we will discuss in the what we call something called univariate problem. But that function can be of like it's a form of the vector. Let's say in a it's something called CNN. For CNN, the input will be the image. So that image, the pixel will like that will give. So it's a 64 by 64 or 32 by 32. It depends on the house. It's going to inform of the vector. So for the vector, so we have the different terms will be there. Like we'll be having something called Jacobian is there. Then we have that. Hessian is there, we have the gradient are there. So then how from there from the Hessian itself, if we do the gradient, and so that we will get the critical point, or maybe the like the points will get. But to get to the nature of the point, so we have to do the Hessian, similar way that what we have done for the second derivative also. So then we came across that expectation also, and then so now today we are going to start like the very classical that the machine learning, like how the machine is going to learn. So if talk about the that one website I'll open, like that is like we'll see in the machine learning paradigm. Like what do you mean by machine learning and all that, how it will go, and what are the types of the learning will be there. So I will just minimize this one. So if we talk about machine paradigm, like it's something that how they are going to learn. Like say we have to that the main purpose of the learning is actually what? Can anyone tell? Purpose is learning to we are going to map from the input to the output. That is something that we are going to do. Learning when we say that input to output, that the mapping will be there. So similar way in the machine that so they can that can be done in a different way. Like it can be a supervised way, it can be unsupervised way, it can be like self-supervised that learning also, or maybe that reinforcement learning also. Okay, so I'll just read out, and if you have some doubt and all, that will slowly will go. So so that the main thing will be that we have to what we have to do the mapping from the input to the output things will be there. So, but the thing is that now we are not much input and output that we know already. Now we want to get the functions. So we have to get the functions and all. So how we'll get it? Like function will be having two parts. Like one will be can be of form the equations, or maybe the weights or parameters will be there. That's the different thing that will comes once we'll go into the machine learning that deep and all. So, if we talk about, so we have for a machine learning, there will be three types of the main data learning paradigms is there. First one is that is supervised. Supervised something that will be having that data will be going to be all label. Then we have the unsupervised learning. We have the unsupervised learning. Unsupervised learning is something we'll be having. Just one minute. That the data will be not labeled properly. So we have to separate the data, and then we have to keep the grouping, or maybe the PCA or GA that can be go in that way that we have to do. Then we have that reinforcement learning. Will be not having much of enough things will be there, but what we'll do, we'll be doing based upon the penalty, or maybe reward based. If that error is more, so we are going to put the penalty. If it is something like it's coming close, so we are going to put the uh, uh, reward based. So if we talk about the supervised learning, it's a very common method that we have actually. It's a very that's a very common that method we have. In that, what will be there? That the system, or maybe something that will be always it's going to say set of input and output pair. So input one, it's going to be output one. Input two, output two. It's something the data will be going to be labeled. It's something will tell okay first part means it's a fatigue data. This is going to it's going to be on non-fatigue data. Okay. So in that, like data will be the labeled, and the goal is to either we have to do the predictions, or maybe we have to get the continuous form. Like if we talk about what types of the machine learning that model will be there. So first one is the classification. Either there will be rain, there will be no rain. Second will be how the forecasting of the weather it can happen, or maybe the how the stock market is going to happen. So it's how things will go and all. So if we want to do like is to predict the weight of the animal from its characteristic, let's say 4 year female, their weight. So that's how it will go. So it's something that we have to do the predictions and all, or maybe the classifications also. So that will discuss like how classification is different from the something like that's called regression. A classification is something that we are going to do binary one, or maybe the multi class classification. Either it will happen, either it will not happen. So if you go into the deep learning, the things and all, we'll see the OR gate, XOR gate, and all. The based upon that, we'll see, and then from there we will going to learn and all. So first one is the that the supervised learning. Supervised learning will not go much of detail of there, but I want to say like if the in that case the data will be labeled, and based upon the label itself, that we're going to find out like whether the our model is going to give the better predictions or not. So still, just keep patience for the one more week this week actually, and from the next week we'll go into much of deeper into, because we are much like we are still on the phase of building itself. So why I'm like keeping the bit of that like pushing, like because why we have that for any model we have that the will be having some sort of parameter that we will discuss for the all model. Let's say for the bias, or maybe that variances, overfitting, underfitting, or maybe other things, accuracy and all. So this thing that we should be aware that how we're going to calculate, how can we deal with the things and all. So once we'll get to know that, so then we can play with the application part. Like we're going to put the architecture, we'll put that labels and all. We're going to going with the with complex that architectures. So if we don't know that why it's happening, like that the accuracy we are getting one, or maybe that on 99% and all. So sometimes it can be overfit also. Why that overfit is happening? That's also we need to check it out. Why underfit is happening, and what is the cause of that? That we have to, so that parameter we should know that. So that's why we are much into the starting phase only. So today we'll much discuss more about that linear regression. So before jumping to the that regression also, we'll see like what is the types of the learning we'll be having in the machine learning and all. Okay, so then we'll be having like unsupervised learning. That is the some. So in that case, second most, do you, that in that case that the data will be not labeled properly. Like in that case, so there will be no either input nor input also. So data is just a set of example. Let's say for a female wild that we doesn't know. So data is not going to label. So first we have to do like we have to check the data. Then we have to do the clustering. Clustering will keep some common parameter, or either we'll do the grouping. That once we'll go to unsupervised learning, that will tell like that the how we're going to deal with the unsupervised learning. So we have to do the clustering. In the clustering also we have different types of the clustering will be there, PCA, LDA, and all that will be there, that will discuss and all. So the today main agenda is that high like that how the data will look like in the case of unsupervised learning. So in that there will no will not able to classify or will not able to differentiate the data, whether it's input, whether it's output, or how the data is going to scattered. So how the data will be scattered and all. That one, many people have to join. Okay, so in that unsupervised learning, in the unsupervised learning, that will be having something called like data will be unlabeled. Then we have to do the grouping or maybe the clustering based upon the characteristic of the data. That's how the things will machine is going to learn, because that the machine is not something that if you feed the data directly, and they will do whatever they want, and then so directly they can go and all. So it will not work like as we think or as a human being that can do. Okay, so it will be going to like do like this. Then after we have the reinforcement learning. Reinforcement learning, that is something some agent will be there. They have done the actions. Then after we are going to put the either penalty or maybe the reward. It's something like I'm just speaking very layman language. Like if you want to have like that much of detailing, so that you can go. There's a book called Bishop is there, or maybe that you can follow that analytics with their one website is there. So here I'm just briefing that what is the exactly actually it is. Okay, so if you see that example, so it's something like the data to learn from the obtained by interacting with the external system, it's called environment. So whatever the environment or the output will be there, from there it's going to learn. Then we're going to put maybe the award, or it's something like it's the that the behavioral psychology will be there. So our interactive learning can be there. So this is the one way actually. Then after, if you go different types of the learning, that is still sometimes they're going to lose. So, but we will have a semi-supervised learning. If you heard about the semi-supervised learning also, so data of the part of the data in the form the input and output pair. Second will be that will call supervised learning. Another part of that will contain either the input or maybe the either the output will be there. So by the name itself, semi-supervised, like it's a half or maybe some parts of data will be the data will be paired, or maybe that properly classified data will be there, or properly that the label data will be there. But some data will be not contained in the forms like any labels or any informations and all. So in that, what we'll do is like so to learn the predictive model from the both of the data sets. Then, if we talk about some another type of the learning that we have, that online learning. So, in this also for the linear regression model that or gradient online learning model is not something that we are going to put something like or it will be learning will happen during the process itself. Like so let's say we are doing training, so based upon the feedback we'll get from the output, let's say the variance is more, so we're going to put some weight, or if that variance is more, if the that overfitting will happen, so we're going to put some penalty. So it will be like simultaneously. Let's say if it is some model, so what will be there? It's going to be like once we start the model, it's going to give some sort of output will get the accuracy, or maybe of some sort of error will get and all. But in the case of learning itself, so in the black box itself, we are going to stream something like it's going to that output they'll predict, and they will try to correct itself. That instead of that user is going to give from the that outside or maybe the externally. It's not like that. It's going to self, and that can be done within the process itself. So it's called online that learning. So then after we have but we have the active learning. Active learning is something like on-demand source of information. Like at the beginning, an active learning process that data will be considered the input. So once a student will be there, input will be there, or maybe that output will be there. So that's how it will go into. Uh, it will be like one agent to the second agent. It will be going to cycle process. Input will be there, then output will come, or maybe some doubts will be there. So it's going to like from the one to second, that the student model can request some of these unknown output from the teacher. A teacher is a system that able to predict the output from the given the input. So it's like active or interactive learning will be there. So then one more thing, but we have a transfer learning will be there. Transfer learning, if you talk about, I'll give you some example. Let's say for two, three types of patients are there. One is the Parkinson that the disease, one is some other disease or that escalating devices that we need to use. So they have done three or four types of the activity they have done. So what we have to do, we have to do the pattern recognition. So now the things will be one way we can do. We'll take all separate exercises or something. We'll do separately. Another way is that, so in that separate way, from the one exercise that we so that we're going to divide that training data or test data in that itself. But once you talk about the transform learning, it's something will be there. We have to we are going to train on the one exercise, but we are going to test on the another exercise. So it's something that way will go. So it's a transfer learning that from the one totally different that activity that will be going to one set of the data, like it's a training set or the or maybe that a testing set will be there, or maybe the validation says that is a set will be there, and we are going to train on the another model. It's something if you're going to for that devices will be there. So what we have to done, like there should, let's say I have that smartwatch is there. Smartwatch, they have the different types of the activity will be there. Sometimes what we're going to build that we're saying, I'm going to do some sort of sprinting or maybe the running or maybe something, or maybe the activity in that also intensity is divided. So that model is divided like this. So they're going to predict different from the activity, or they're going to find out the from the pattern itself. Then the model will say, okay, this is this time they are doing this activity. So it's a transfer learning. We are going to mix it up with the different types of the exercise, and then we are going to get to some sort of that devices and all. So it's a transfer learning. So it's a something transfer learning is the details of like transfer learning deals with the transferring knowledge from the one learning task. One learning task, like I told, that's going to be a walk to the another learning task. It can be a running or maybe that weightlifting and all. So that's how it will go. So it can be like from the 1 2 3, then it will go from there. So that's the one, that's the different types of the learning that we have. Then another type of the learning that what we have is self-supervised learning. Self-supervised learning, in that refer to a supervised learning problem for which the input and output can be obtained from the data itself. Let's say we have a data is there. So without needing any annotation or maybe something that from the user side, we are not going to give the any label. Will not give any labels. But the thing is that what they will do with a model, they're going to find out what is the input, what is the output based upon their own by their own. So that's how it will go. So that's the different types of the learn that what we have, and mostly in that also auto encoder and generative and then trust learning and all that we'll see in the details and all. So now today the agenda, we are going to start with the linear regression. In that linear regression, that we will see like how the things will go, what are the functions are there, and then we'll see the bias, then the variances. These two factors very actually very important. Then we have goodness of the fit, that one terms that we are seeing very frequently. It's called a r square. That is a coefficient of determinations will be there. So that's a very frequently we'll see. So that also we'll see to like today. Then we'll see like what are the different types of the linear regression that the models are there. Okay, so we'll start the things now, and we'll jump into the like that's called. Okay, so we'll close it up this one, and we'll come to the PPT directly now. Well, if we see that in the first class itself, that what I have demonstrated, like we have a different types of like classical programming, what they will do, where we having some sort of rules will be there that's already defined. Let's say the chess, that example we have seen, is it? So in that rules are there, datas are there, we'll get the answer whether who's going to win, who's going to lose. And we have the different types of the some sort of games was also there. But in the case of machine learning, what is there? The data is there. And answers will be also there. Like it's a input and output, both are there. Now we have to find out the something called the rules. What can be the rules? Maybe what is the functions, what is the weight, or maybe that what is the cost functions and all will be there. So that's how the things will work. And then after they're going to do the prediction. That will be the one with the ground truth, and one will be the predicted one. From there, we'll get a J. J is something called, say, error, or maybe the cost. Okay, so we'll get something like this, and then if based upon that, if they're going to give the feedback again here, so it's a feedback. So that's the one way of learning. So if we talk about the we have the different types of the learning will be there. If it is come to the specific to the process, we'll say. So forward learning is something will give feedback. Then second one will be having the backward learning. that the backward learning will be there. So in like for the linear regression cases, what we'll be having, let's say from the x what we have, we are going to predict the y. Like y is equal to mx plus c. So for the given x, what is the y? So we'll go from the x, then we'll get the y. If the same cases, if we have the y, already functions are there, we want to get the value, so we'll go, we'll be having, we'll find out the x, so that will say the backward learning, or maybe if you see in the case of AN and all, so in that also feed forward and then back forward will be there, and back propagation and all will be there. So I'll tell you the one classical example in the field of biomedical. Like we have the two different types of the learning will be there. First one is the back, like forward is there. Let's say I'm going to give some input, the velocity and all that will get some forces. I'm going to run. We have some kinematic data is there. We have the signals are there, and we'll do some post processing. We'll get the corresponding joint force. Okay. But second case, what we have already the joint forces are there. We have the already forces that is the ground direction forces are there. Now we want to get like what is the kinematic parameter will be there. It's coming from the back, like from the backward. We have already the outputs are there. Now we want to get the input, like how what can be the our input value. Let's say why this is going to be more important. When we go into the medical devices, like to support for any of the patient, let's say, so we have something like how much of force we can apply. Let's say how much the weight can apply. But the thing is that that is so corresponding to that force, how much the kinematic or how much they can walk. So for that type of, like, we have to get for this much of weight, for this much of the force, or this much of the joint reaction, how much they're going to move, how much they, so they're going to move the kinematically. Like kinematic, like it's something, what can be the angle of the rotations will be there. So it can go in either way. So if someone is from the background of the biomedical devices and all that, so that something the idea that so that you will be having and all. So if you are much into that, that we'll discuss later part also. In the ANN, we'll discuss the both side of that way. That is that is the backward propagation and then forward propagation that all will see. So what is the things is like, so if we talk in the general, so we want to learn little between the input and output data. Okay. But the thing is that, so before that we have to, so what kind of relationships are there? So it's something called parameters and a weight. So it's something like the functions will be there. So that function will say y is equal to mx plus c. So that function will say hypothesis function, or maybe that our initial function will be there, or maybe the model will be there. If you talk about general model, y is equal to mx plus c, but we'll go with the w transpose x plus c. So it can be applicable for the reinforcement learning also, or maybe that the linear regression also and all. So it depends on the what is the t that the t value will that we are going to giving and all. So if you talk about that function, so in that we'll be having two types of the two type that the two parts will be there. That the one part, it's called the form of the function. Form of the function is something will tell either it can be a linear, the quadratic, or maybe the logarithmic, or maybe the exponential. So that is something called the what form of the question that we are going to define. We are going to define. Then after the parameter of the functions, it has something will tell the weight and all. So that is going to do the prediction with by the model. This form we have to decide, or we have to give the input. So that's why whenever any of the machine learning things, so we should have the domain language. So that's called a domain knowledge should be there. Let's say a person is saying that I want to predict the fatigue in the case of the pipe also, or maybe that screw nut also, or maybe the person getting fatigues and all. So when the fatigue will happen, what is that relation? Whether it's going to be like truly uh, linear, or it's following some sort of nonlinear parameter, or maybe that cubic, exponential, or some others and all. So if a user doesn't have this knowledge, so they can't go or they can't get the better that the model. So there is always chance of the error will be there, and they're going to make is like they're going to make some sort of mistakes will be there. Okay, so that's how the things will work. So before jumping directly to the our machine learning models and all, so we should have that what are the applications, what is the input, what is the output, what from the input to the output, what is that relations is there, or how the things like form the functions will be there, how it vary with the x to y or y to x. So that is the one thing. Second thing, that parameters are there. So parameters that we will define based upon the whatever the output we got. That can be of learning rate, or maybe the epsilon will be there, or the error or the biases are there, variances are, so that we can play with that. This is the another things. First thing is that we should have the like a domain knowledge, so that we can say, okay, that my model is going to follow like this. If I'll say for the fatigue, a person is going to start. Let's say they are doing the running. So what they will do? This is, let's say, distance or maybe time, and I'll say the fatigue, or maybe the speed. I'll say forgot about the fatigue and all. What they will do? So they're going to start with the high speed. It will go maximum, and then at certain some point some fatigue happen, or they got tired. That the fatigue is nothing, is something called like tiredness, or a person muscles that can't generate the force to keep to maintain the input whatever we need to keep for the speed. So fatigue happen. What happened? The slowly that the speed got decreased. So that is something the domain knowledge I have, so that I can define, or I can like give the form the functions that I'll give it. So to get this exact replica, or maybe the mechanism for the fatigue, so for that, we can get the parameter for the functions. Like it can that we can play with that to get the exact. Let's say this is going to be a actual. So for a given parameters, we are going to do the predictions. So this prediction line we can give with the different learning rate, error, bias, and all that we can give it out. So before giving, or before we want to get the output or to get the functions, the forms, we should have the idea of that. So that's why, so that the that so that the learning can be done with the machine learning. Okay, so that's how the things will go. So that's why I'll be saying, like, if you have very clear idea, or maybe you should be very clear about what are the things that you're going to do, because if you do the experimentally for any other domain, like it's in mechanical, so I'll tell for that much of the load, that much the deformation came, or for that much of pressure, that much the stress came. So that is something that input I'll give the, so that the output I'll get it. So, but the machine learning is what they need the input also, they need the output also. So not the things is that so you have to do the fine tuning. It can be done in a different way. So that's why you should be having very clear the things, like how, what is the input, what is the output. That is the only simple thing I'll say. So in that also, uh, so in that forward modeling, what will be there? We'll be having the x, that is the input, and the corresponding weights will be there. In that corresponding, that the weights will be there. Then we'll get the some sort of functions we'll be getting. So that's I already told, it's a form of the function that will be the either the linear, quadratic, exponential will be there, and second can be the parameter. So for a given x, choice of the w, we can find the correspondingly y. So that is the one thing that will be there. Let's say y is equal to w0 plus omega 1 x1. That is something will be there. So we'll tell, okay, for given x, y, we're going to make it like, let's say, for x is equal to 0, we will going to assume 0 as 0. Then we are going to do the that updation in the current, and on that for particular things will get it on all. The function f going from x to y will call the forward model. In the same way, if we go from the y to x, we'll tell what? We'll tell what the backward model. So that's why so that's why I'll tell, like, both are important, but the thing is that we should have the idea like where it going to use and all the things will be there. Then after, if we talk about like how the things will get learning the parameter that the via the feedback, I told like we have the x are there, we have assume something, then we have make the hypothesis function. For that also for the ideal cases, what will be there? So there will be no error will be there. But in actual cases, what will be there? We'll be having a ground truth that is a y, but they're going to make some predictions and all. From that, we'll get some sort of error. So that is always the chance that we'll get the error. Sometimes the error will be high. There's sometimes the error will be the low. The thing is that based upon based upon the whatever the error we got, we are going to give the feedback, and then we are going to improve W by the gradient descent. So then we'll get the things up to what time? Like up to we have to minimize the error, or the stopping criteria is something that will going to minimize the error will should be there. So that is the one way. Like we'll go. Let's say for a initially we have assumed something, then we'll keep in. So it came uh, W1. Now we'll keep W2 will come. Now W3 will come. So until unless it will go, that error should minimum, because it's a something we are going to assume will start the iteration at the 0 0 or maybe 3 3. Let's say I want to get that actual value that I'll take one for example also. So in that will be that will start first iteration. We're going to that make assumption. Let's assume omega 0 is equal to 0, or maybe the 1 or 2, something will be there. But then after we are going to do the correction or update based upon the what we got, the error, or maybe that gradient descent will be there. So that's how the things will work in the feedback that the model. Similar way, it can go for the that's the backward model also. So for a deep learning engineer, what are the things they should have the idea about, or the things appropriate decision for input and output vector. So what is the x, what is the y? They should have the idea, because all problems are the data, and that can be mapped into the functions and all. Because that one x, one y, but how it's vary x that how vary x like that the y with the x when the x y is equal to mx plus c. If we change the x, how that the y will vary. Then after choosing the appropriate data set, that's also very important. That data should be not very small data set, or data should be not much of noisy also. That the noisy, it comes in terms of many things. Noisy means like we have the too many variabilities are there. Let's say we want to check either that old and kid, maybe that elder and kid. But the thing is that if you keep too much buffer, let's say 0 to 5, one type of kid, 5 to 10, the secondary kid, then 5 to 10, then it become the adult. Then for that the elder also we keep a 40 to 50 something. So we are giving much of variability or the complexity, but things that in that also, so that it can become the overfitting also, underfitting also. It depends on like how how the bias and variance is going to vary. So, so that's why the choosing the appropriate data set also very important. That the simply so we will not tell like we have the too much variabilities are there. So we're going to apply the complex model. We'll get the better results, and that if we come to the directly to that prototype, so we'll get better that accuracy and all. That is not always the case. We have to simplify. We have to normalize, or we have to check. Just 1 minute. Is it that getting bored, or it's able to clear enough? Can anyone give us some that the feedback? So they slow down. Okay, thank you. Then after we have to choose the appropriate model also the same so that the same way I told it's a linear model or maybe that a quadratic model or maybe that logarithmic models and all that we have to check like properly. Then after the form of the long that long like something called loss function. One that the very common methods what we have it's a least square method. In that also we'll be having different types of the list square methods and all will be there. So then after we have to choose the optimization algorithm also. So it's something called gradient descent one is there something. Then second one like in that also gradient descent algorithm also we have it's a momentum is there and Adaport is there and add-on like something another more types of the model is also there we have. Okay, so what are the things that we are going to look after into this week? Like we're going to see each of the this have their own purpose and where they work well. If it is going to that's going to be a linear regression for simple polynomial regression analysis. It's something will have the forecasting. Let's say for the house with the price with the time how it vary. It can follow that something linear also or maybe the exponential also. Then what we have a logistic regression will be there. It's a for two class classification problem. For this house price, that's a one with the one. It can go with the simple model will be there. So that we can follow the linear regression. So in that also we'll be having the polynomial fit will be there. First order, second order, third order that we can play around with that. Then what we have, it's a logistic regression will be there. So for two class, it's either that so that the rain is happening or not happening. Yes or not. Okay. So if there are two binary classifications, like it's a spam or not spam, so it will come the LR or maybe the binary classification or not. Then what we have, it's a there is always the things will be there that that the real life problem, it will be not the always the linear. It will be the always the non-linear problem. So to deal with that and all that we have to check with the deep neural that the network DNN will be there. Then after but we have a CNN will be there. Conventional neural that the network it's based upon the vision or image based. Then what we have that RNN. RNN something recurrent problem like it's a sequential or time series problem will be there. So it's whenever we will be having let's say the fatigue how the fatigue progression is happening with the time. So stock market it's actually that we can deal with the temporal that the learning and all that will be there. So for the each model, for the each and then we'll be having different appropriate loss that the loss function will be there. So sometimes that RMSE is there, or maybe that the mean absolute error is also there. So that's why so we have to be very clear about that also. It is possible that you might have better model than this of full problem. So, but the thing is that output or maybe the outline will be the same. Let's say I'm saying like I'm going to for a simple forecasting also I'm going to use the LR. It's a logistic regression that might give the better results also. And I'll say I'm going for the linear regression. Someone can go for the LR also, or they can so they have went for the exponential also, or maybe the DNN also. They can get a better parameter. But the thing is that whole structure, whole the pipeline from the starting to the output, it's will be the same. Outline will be the remain same. The thing is that we can play with the black. That's called a black box. Till now, what we are doing, we have the input output. We got some that is the predictions or error. So in this course, what we are trying to learn, it's a, what's inside the so that the black box, where we can play with that's called learning rate or the parameters or maybe the functions itself, we can play with that. So that's all the things in this full course we'll see around. Then second one, what we have, then we're going to find out like how these of the model it's going to with the time it will going to like discuss and all. So first one, if you see for that linear regression, what we have, it's called mx plus c, and the logistic regression, what we have, it's a sigma mx. So it's called a sigmoid. Sigmoid, it's a non-linear parameter. If sigma become 1, that sigmoid function will become 1. So it become a linear problem, linear regression problem. So that's how the things will go. Then what we have, what is the good loss functions? That maybe that cost functions, not cost function. It's something loss function will be there. So first one I told like it's a least square. Second one can be the entropy. Entropy, like how the can anyone define like how what is the entropy actually for a model? If I'm saying that the entropy should be less or high. Oh, the same way that I'm saying the least square error, or maybe the error, it should be less. And if I'll tell the definition of the entropy, it's called something called entropy means randomness in the system. For a for a model, it should be stable. So means there should be no instability or no oscillation should be there. So means entropy should be less. Entropy, if we define, it's the randomness in the system. If any of the system that if they have the more entropy, it means that is the unstable system. Unstable system, like it's going to make changes will be the more. Even slight change in the one parameter, it's going to make the drastic change in the output. So we should be very careful. Like it should so that the model that I'm talking in that the room itself, if the entropy is more, so there might be of that the heat will be more, like that the person will get sweat also, and something will be there. So that the one change will cause the it's going to cause the major changes in the output and all. So that the similar way for a model, machine learning model. So if I talk about the entropy, it should be less as much as possible. So if we talk about till 2020, like till the COVID, people were talking more about the entropy, or maybe that is the least square error and all. But now people are talking about the uncertainty also. Let's say I'm going to predict also something, or we have checked with the that the error also. So whether if I'm going to do the like how accurate, how certain that the our results are correct or not. So if you talk about that the recent paper that is uncertainty aware, so we'll get the stability index. So stability index that comes from the entropy itself. So that is the one thing that will come came across something new that based upon that will be coming that the advancement of the machine learning and all. So that will discuss also if time permit in the 10th or 11th week also if time permits and all. Okay, so after that, what we'll be having like, so to calculate that also, so we have to calculate the gradient. So that's so that we can calculate the gradient that we have seen like before the class also and all. So now we'll come to the actual linear regression problems and all, how it will look like and how it will go from the here and all. Okay. So if we talk about the linear regression, so the things will be linear. First assumption will be something called linearity will be there. And if you talk about a basic like a difference between the what is the classification or regression, it's something that discrete or categorical that I told is spam or not. That's going to be not a spam and all. Or maybe it's going to fit data. It's going to make with the time. with this changing, how it's changing. And if it is going to make closer to the ideal line like this, so means it's a good fit will come into the picture. So that's also we'll see like how the good fit or coefficient of determinations and all that we'll see also. So it has going to category associated. Like it says something that I told, okay, this group of the people, second group of the people, but in this case, it's going to be like with the one number, how it went, it's going to be seen like this and all. So if you talk about the tumor classification or maybe that spam classification, in this also like a stock market is there, fatigue predictions are there with the time how the fatigue is happening, or with the time how the forecasting of that the housing rent is happening. That's also we can see around and all. So before that, what we'll be having that will be we have to check around in that case also. Input will be the x, then output will be something called y. Then after the model will give something y hat. Is it? So that can go in that way also. Now we have to get the error. So error will be that y minus y bar. Okay. Then after we have to, we have to get the mean square error. It's some sense that also will get it. So that is the one cost function can come. So for that the cost function j is equal to 1 by 2m. Let's say whatever the value that actual ground truth are there minus whatever the model values are there to the whole square. So what are the things that we have to do? Now we have to like to get, and we know that wx plus b, or we'll tell omega naught plus omega w1x. If we keep this value, and to get the error less like 2, we have to get the like credit descent should be delta j by w0, delta j by w1. Then we'll get the value. Then we'll try to get the as minimum as possible. So now once we got this, once we got initial values, what we'll do? We are going to update it. Omega 1 is equal to omega 0 minus alpha, and unit descent. So once we got this value, so we'll go omega 2 is equal to omega 1, like w1 minus alpha, and this is going to be a gradient descent. So this alpha is actually what? Alpha is the learning rate. So that's how the updation will going to happen and all. Okay. So that we have to find out the value of that which weight parameter, what will the error will be the less and all. That's how the things will proceed and all. Okay. So if I talk the in general, what will the steps? I'll take one page actually. If I talk in general, just 1 minute. Linear regression procedure. So first is that we have to decide what alpha and epsilon and the stopping criteria. I think we have talked the last class what is the stopping criteria. That is something that J of. Then after we have to make the initial guess for the weight vector. Okay. After that we have to calculate the next weight k plus 1 omega k plus alpha by 2m summation of I is equal to so if this thing like satisfy the stopping criteria, so we have that weight, so that corresponding to that weight will be optimal. That is if not satisfied, if not satisfied, so we have to go to the this step. So that's how the things will work in that. What you can say in the context of that the linear model and all. Okay, so now we'll see. These are the specific to the what you can say linear, and now we'll try to figure out generalized linear regression model. Generalized function for linear. Just 1 minute. Okay, so what will be there? We have to find out the what is the input will be the x. Input will be the x. That is the size of the x will be given. Then y will be the output vector. Then after alpha will be the learning rate, and epsilon will be the stopping rate. And there we have to get the w, the weight vector. W1, W2 till Wn. So in that also, now what we have to do, we have to, but the things will be, we have to define the cost function. J is equal to hours is the 1 by 2m summation of yi minus y hat square. Once you get that, from there we have to get the gradient descent delta j by delta omega delta j by delta w1 till will come delta j by wn. Okay. So once we come here, so we'll get the w value. Then we have to update wk plus 1 is equal to wk minus alpha delta, or maybe I'll say gradient till k. So that's how the one generalized form is there. So before jumping into the we have to, one more thing is there, that is the rescaling or normalization. Uh, Anyone have heard about this? What do you mean by? I'll just take one more page actually, two more page I'll take because that's I have to discuss more things. So there is one term called rescaling or normalization. Why do we need the normalization? Can anyone tell why do we need actually? Rescaling. Rescaling or normalization something. Why do we need? Because if you talk about the real-time data and the data and all, what will be there, that the magnitude will be very high. Magnitude, it will be the very high. So, but the thing is that if we take for the model that can be taken, there is no issue with that. But sometimes what will happen, it might create or it may behave differently if you go and fit the data. And if it is not giving the proper things and also what we'll try to do, we are going to that normalize the whole data into from the 0 to 1 itself. Okay. It's not like, let's say I have the data set from the minus 10,000 to plus 10,000. But it's going to make like some sort of it will going to give the greater storage of data also. And but like if we are going to make any slight change or if things will so that will not go in our way, it will going to create some that the model will behave differently. what we'll do, we're going to do the rescaling. Rescaling something will do x bar is equal to x minus x minimum by x max minus x minimum. So it's going to belong to the 0 to 1. So it means that's going to belong to the 0 to 1, 0 to 1. So that's the one way. Second way, if you have heard about that the normal distribution. So in that case, it will behave like x minus mu by sigma. This mu is nothing but a mean. It's a standard deviation. Okay. So this process will call normalization. Okay. And this will call rescaling. So why do we need? We need to like simplify the data, or to if we're going to give the input to the model, it should be simplified. Data should be there. So that's why before giving to the any input data, we have to do the normalizations and all. Even let's say for my case, like my research area, that something is this. I will going to conduct some study that the fatigue will happen. But for my case, I will going to fatigue in 5 minutes while I'll do the sprinting, or maybe I'm doing the treadmill with some certain speed. But the same speed, a different person, that the different person will be going to fatigue in the 4 minutes. Some is going to fatigue happen in the 6 or 7 minutes. So the thing is that it's going to that the length of the data is not going to same. Length of the data for me is different. For second person is different. The third person is different. So in that case, so we the things will be, so in that case we will going to do the get the common length of the vector, like timing or something. So we'll do the something called normalizations and all will do. So from there we have to. So that's a, if we give, so there will be chances will be there. So for my case, I have some sampling rate of 2000. For my case, the data came 10 lakh. For some, the sampling rate is same 2000, but the data came some 15 lakh. So what happened that the data is going to make like it's going to imbalance data. So either we have to make the balanced data by putting some weights, or we'll do the normalization. That we'll see that how we'll deal with the imbalanced data also. That's on all. So that's why before giving any input to the things, that we have to do the normalizations, or the rescaling. If some places, if the model or application is very specific, is something that, so that we don't need for the rescaling or the normalizations and all. So that's why if the data is very noisy, for my case it's a signal processing data, like it's a electromagnetic data from the muscles will get very noisy, very small in the magnitude. So I have to do the normalization. In some cases, like let's say I'm going to put that much force, that much weight, like that much deformation came, so there might be not require the normalizations. Sometimes it require if the number of trials are more. So that's why we have to see like how the things will going to work out. And before going into the defining into the input vector or output vector, we have to do the rescaling or the normalizations and all. So now, like then what we have, it's a, if we have done the linear regression, so it's going to make the predictions. Let's say we have that data is there. This is going to be ideal case. That the things that after predictions it came and all. So how good the fit are there? Let's say I've created the linear regression. This one, first one is the ideal. This one is the predicted. Or we have done the quadratic also. Maybe the cubic also. So it's like what is that is how good the fit are there. Like it will check with the goodness of goodness of the fit. Is it? Yes. So now the thing is that that's what good is of the fifth. It can be done with R square. R square is something called coefficient of determinism. Okay. So let's say what we have the quad function, what we have. Just 1 minute. So if you talk about the R square, so their range will be 0 to 1. If it is going to close to 0, it's a very bad. If it's coming to the close to the 1, it's a best fit. Is it? So in that what we have some terminologies are there. I'll take some I'll take. Okay. So in that what we have some terminologies are there. Like let's say this is the one thing. This is the ideal case. This is the predicted data came. So we'll take like this here y came. Corresponding this here, this is y dash. Then after, if you talk about the error, it's a y. So error will be there y predicted. So if we calculate like SST total sum of square, it will come like I to m yi y bar to the whole square. So it will give what amount of variance present in the data. So then the second term what we have SSE. I'll tell you like how it will look like. Summation of 1 to m yi minus that what we predicted from the model. Okay. So that then the third term what we have SSR regression, summation of 1 to m, that the model itself minus total data. It's a sum of that regression. Amount of the variance captured by the model. So that is the one thing. So R square, if we define what S is R, the amount of variance captured by the model by amount of the variation into the data. S is T. And if we talk about like how it will go, S is T is equal to S is E plus S is R. Okay. So R square actually effectively it will go 1 minus S is E by S is T. So this is the how things that's called goodness of the predictions. It's all talking about the variance and all. Okay. So then after what we have, we'll be having something called overfitting and underfitting and all. So that one things will go when the variance will be the high, the when the that when the bias will be low and all. So if we talk about that underfitting and then the capacity and overfitting, how it will go. So the thing is that underfitting is also is not going to good for the our model. Overfitting is not going to good for the our model. So what we have to check? We have to check the appropriate capacity. It's something that may be the quadratic itself, or will if we increase the our polynomial like a degree of the polynomial, it will going to fit. But the thing is that it will make the variances will be the high. When it's like that, in that case, the make the capacity is something that make the training error small, make the gap between the training and test error should be the small. What do you mean by this thing? So if I'll show you the one figure like what we have, so this is called like optimal capacity, and this is the training error. If you run the ANN or something DNN in that in the MATLAB, so then they're going to check one that validation curve and then the training loss and all that will checking. And if when the capacity is going to increase, when the capacity is going to increase, so what will happen? When so it going to like the training error, it started at the top, then it came down, then it become the flat, and then it will go zero. But the generalization error also it came down, it went somewhere here, and till here it was something that the gap was less. Once the capacity got increases, that the error got the gap got increased. It means the variance got high. But here, like so at this place the gap was low, and then before the optical capacity, so there was a case of the underfitting. So we can control the whether the model is more likely to the overfit or underfit by altering its capacity. Let's say for a polynomial fit, first order, second order, third order, fourth order, fifth order, that will go. So that we can check overfit is happening or underfit is happening. If we take the if that any things are that vary the quadratically, but we are giving the one like linear regression, so it will go to underfit. But the thing is that it's going to perfectly fit or the error is less as compared to in the case of what we can say that predictions. But what happened? We are giving three, third order, fourth order, fifth order. So what happened? That computational cost is going to increase also, and that the variance is going to go so going to increase also. So that will not also make the sense also. Okay. So this is how things will work for the underfitting and that is the overfitting. And this one will call optimal capacity. It's an optimized value. So that purpose or that is the main agenda for the machine learning is to find out the optimal parameter. The thing is that in some cases that if you read some problem for the machine learning like that machine learning papers and all, so they will do once they will do some sort of model testing and all. They came with the results, but then they will do the what that's called a hyperparameter. What they have done, it was either underfitting or either it was getting overfit, They have done the optimization using maybe the GA, like it's called genetic algorithm, like something, or so that the PCA or something they have done, and then they then came across with that. So it's called we got the optimal capacity, then the error was less, and then in that case the accuracy got to increase, error got like this and all. So now the things is that what we have two terms are there, bias and variance. What do you mean by bias? What do you mean by variance? Can anyone tell? Bias, high bias and low variance. Bias means like it's either it can be our prediction should be come here. But the thing is that it went somewhere here, and means the gap is more, so bias is happening, and the whatever the all the output we got from the all that particular model itself, so means the variance is less. It means this was the predicted value, but we have done the first time, second time, third time, fourth time, the fifth time. It came. What happened? It's like that particular value we got. So variance become less, but the bias is still high. Now, so now the second case what we have, it's a high variance, high bias. So it's not going to fit at this point, like at that our what we need at the ideal case. It's going to randomly, it's going to away from this point, away this point, and it not going to close at one point here. It's so that the first case as it is here, it makes something. So it's called a high variance. High variance means like there is a oscillation is happening more. Oscillation is something one at there, second at there, second at here. So it means high variance. Then after what we have, that's called low bias. What we have the ideal value, then the predicted value we came across, it's coming closer to that. So means low variance, low bias. Means there is a error in the less. So when the bias is high, it will happen underfitting. I'll tell you like in the coming slides and all. Then after what we have, like then the like the point output is closer to the ideal one, but the changes like it's that not coming at that point. Like it's not coming closer to that, but it's making one time 0.001, 0.02, 0.001, something like this. It making so it means low bias, but the variance is high. In that case, it will going to comes under the overfitting zone. You know that I'll tell you how the things will go now. So if you talk about so the model complexity will depends upon the bias and variance. Where the bias is happening more, where the variance is going to happen more. So then that can play with the error. When the bias so, model complexity is nothing but the number of parameter and bias function used in the model. It's a totally the model complexity is all going to depends upon the bias and error, like variance, and if from that it will come the error. So whenever it's going to bias is going to high, it will happen the unfit, and then so that the variance is happening. So means again it's going to be a like that overfit and all. So that's how it's going to reflect on the error itself. So now I'll tell what is the bias. Bias is actually nothing. Expectation value of the difference between the that the predictions and the correct value. Okay. So means bias is equal to expectation of what we have predicted, what is the actual correct value is there. So that will say bias. What about the variance? Variance that we already know, expectation of that what we can say that we have the predicted value, then average of that what we can say the summation that so that is square will be there. So plus error will be there, or maybe the noise will see that just to keep in the track or check that it should not behave very blatantly, and also that will add the noise in terms of the epsilon or something will be there. So that will see once we'll go into the model and all. Now we'll see how the bias and trade is going to happen. Just see, like let's say that the bias and variance move in the opposite direction as model complexity change. Model complexity is going to increase error. So this is the case of total error, and this is the case of variance, and this is the case of bias. So this is how things will go. It's going to like opposite direction as model complexity change. Just 1 minute, just come. Till here, if you have any doubt, please, just write down in the comment. I'll just play.
Uh,
Any doubt is there? Till now it's clear? Okay, fine. I'll go ahead with that content now. Okay, so if you talk about that, how things will go, it's a bias and variance is going to move in the opposite direction actually. And when the model complexity will change. So when that model complexity will change, what will happen? Variance maybe it will come higher or maybe it will go lower also, bias also. So the things will going to change like when the low complexity means high bias is there, then that what we have, that low variance. Variance is the low, bias is high. What's happening? It's going to underfit. It's called underfit zone. Then what we have high complexity, low bias, but the variance is going to high, we'll say overfit zone. Then optimal balance that minimize the total error. So that's the thing that our agenda will be there. We have to minimize the error. Always we have to minimize the error. So if I talk about like much of more detail, it's the bias is actually underfitting will happen, or the variance case overfitting will happen. So whenever there is a like underfit is happening, or the that so we'll tell okay, so bias is less. No, that the bias is high. Okay, so that we can go and change the parameters and all. And if the case of variance that the overfitting is happening, so in that case the insufficient features are there. What happened? For to give the optimum parameter, optimum models and all, we didn't give the enough informations. Okay, what happened for the underfitting? We need to give much like optimal information we have to give. Means we didn't give the much of information. So what happened? It going to happen to the underfit. But for the variance is high, what happened? What we have got too many features. I told one example. I have to classify either with the kids or with the elder. But what we have done, we have a sub-classify we have done. That 0 to 5, 5 to 10, 10 to 15, 1, 3 cases. That's a too many features we have given for the kid also. And for the elder also, we told 40 to 50, 50 to 60, 60 to 70. So we give that we give multiple feature. So there is also that, so that causes the overfitting also. Okay. Then simple that model might have the high biases. Let's say the thing is that what we have like stock market prices is there, it's a highly non the model. But if any of the novice, those who are trading, whatever, so they have drawn the straight line. Maybe and then that's something they have predicted, but they got the huge loss. What happened? So they got like high bias. That the error is very high. Then after simple model might have the low that the variance also. The thing is that it's going to perfectly fit also sometime. So that's why it will make sense, but it's going to something overfitting also. Complex model might have the low biases. Complex model might have the high variances also. It will go in the like just opposite cases and all. Complex model with many parameters might have the small biases, but the large variances. It's again like it's both are complementing always, and there also simple model with a few parameter might have the large bias, but the small variances also. So there is a both possibilities are there. So we don't have to much think about that. Like we have to think about whether there should be not much of input also, and we should not give the very few parameters also. So it will be high chances that it will that the model will not give the accurate predictions or maybe the classifications and all. So it's again the same thing. An underfitting zone just right, and that is the overfitting. It's something if you're going to give the complexity, we're going to increase. So what happened? The variance will be it's going to perfectly fitting at the 1 point, second point, 3 point, 4 point, and all that's the it's the overfitting is happening. Preferred if size of data size is very large. Underfit, it can prefer if the data size is very small. So increasing the bias reduces the variance and the vice versa. That's what I explained that with the figure. That's one is the bias. That's how it's going, and this is the how the variance is going. So error is actually bias plus variance plus irreducible error, that will say noise. That's what we have to add something in the signal. We will be having that white noise and other noise that will keep the adding and all. The best model is where the error is going to reduced. It's again bias and variance both are not complementing, like it not complementing. It's something that's opposite, that the behaviors are there. But the main agenda is actually what we have to do, that the error should be reduced. Compromise between the bias and variance. Like it should be like there should be no that the high bias plus the very low. So we have to make the optimal balance between the bias and variance. So that's how the bias and variance will trade off. So that's how the things will go. So this thing we have to be very careful. We have to know that okay, where the variance is going to happen, like it's happening more, or the variance where the bias, so that the bias is more. So we have to play with that also. Then after it's like how can we fix the bias and variance problem and all that we can check it out. Initial split of the training set is insufficient. Like how the things will go. In order to handle the bias problem, we need to have the following the split of the data. First one, let's say like if you see that how the training is going to happen, training on a split. So we'll say training set is going to 60% of the data. So that we have the 60, that the 100 data is there. 60 is going to for the training. So that is going to learn the optimal parameter of the given model. They're not going to use for the validation, not going for the training. Testing. This is actually a testing set. Okay. Then what we have a validation stage, we'll say to 20%, 60%, 20%, then again 20%. Either sometimes we'll say training and testing. So 80 by 20, that's a simple things, that 80-20 rule that we're going to follow it up. But sometimes we're going to split in the like in different way also. So validation or like a development set will be there that are going to not used in the training. You should test the quality of the trained model, bias or variance determinations. Like we can play directly within the model itself, bias and variance. Then we can come up with the hyperparameter. That's how the things will go work out. Then we have the like testing, not used for the training or validation, used to determine the efficacy of the final model. We'll say we have done the testing on the unseen transfer learning. We have transfer learning. One problem is there. We have taken one different particular exercise. Second, we have done the one on training. Then the second we have took, and then we have done the testing on that particular things. So it's something. So that one data is not going to use for the another one. So testing is actually for the how good our model is there, or how efficient our model is there. So the same thing here, training error, validation error. So training error magnitude is going to be high, means the variance will be low. Similarly, the context or something will be it's actually different. Like it's the terminology is different. So then after validation error magnitude similar to training error, high compared to the training error. So to deal with that, actually, what we have to do, we have to do the regularization. Regularization is something that to overcome the overfitting, and that is done how it to penalize the large coefficient. I will not go much of detailing of this. If you want to go with this, so that you can follow the Bishop book is there. So that the agenda for this is that to keep training and test data closer by keeping the optimal regularization parameter. It's something this range will say. So the thing is that there should be no like very close, and there's something. So it's optimal parameter. Like it should be data closer by keeping the optimal legal parameter. So that's how the regulation will be done, by penalizing. Let's say I have different types of the like datas are there, but one few data is going to acting as a outlier. Outlier is something very differently. So what we'll do? We're going to keep the weight on that, or we're going to put that penalty on them, so that it will come on the range of let's say I have the data 1, 2, 3, 4, 5, 6. But suddenly one data is the 50. So now to keep the range of 1 to 10, what we'll do in the keeping the weight. Weight means penalizing maybe zero point 0.1, zero point 0.2. So that's all the things will go. That's called L. It's L, we'll say L1, L2. It's called regularization. That's the term we call regularization. So the thing is that we have to penalize either 0.1, or either we have to magnify, or either we have to come closer to that, but we have the range of that. So that's how the things will go on. Then what we have the gradient descent algorithm. So we have a different types of the gradient descents are there. One is the batch one. Batch one makes the parameter update, cost function, use the train intercept, no all update possible. Like we'll take this is a new, this is the previous one, this is the learning rate, this is the gradient. So that is the one thing will comes into the picture. So that's called batch gradient. Second one, what we have that stochastic gradient descent. So they're going to parameter update are done for the every training sample. Means in each step itself, you have to put like that the updates can be done. Then here that the online learning is possible. Like it's something that will going to in the process itself we can update. So that the gradient descent we call that stochastic the gradient descent. Then what we have mini batch gradient descent. Combination of the above perform update for the mini batch for training data. So that's the one thing. Then another type of the algorithm what we have, it's called momentum. Then second one what we have the nag. Then what we have the ADA grad, and then ADA delta is there. So in the momentum that I told, it's going to add a fraction of the previous update to the current updated. It's called something like this. The delta will be there now. It's going to help to take the largest step in the relevant direction, preventing the oscillation and problems and all. Then second one what we have is the nag. Nag is the actually it's going to from the future they will going to take it out and then they're going to update it. Like it's not from the previous, but it's going to take from the future itself. Then we have the ADA grade. It's a that we're going to use the different learning rate. Earlier, we were playing with the weights. In the ADA grade, we have to play with the learning rate. Then what we have the ADA delta and then RMS group. It's again extension of the ADA grade itself. In this, the coverage will be there more of the squared gradient or the weighted average we have to take care. So the thing is that we'll see. So now we'll solve some problems. So can we see one problem? So what we have, given the n data points with the m feature, suppose we have to hypothesize the linear model such that this is the uh, like uh, plot function is given or the hypothesis linear function is given. Linear function is given. Now what to do? Suppose the that loss function j is the emission function is given by like this. So where x is the design matrix, y is the mode of prediction, y is the ground truth vector, w is the weight vector. So they're asking expression for the optimal value of the w will be. What will be the optimal value? To get the j is given. To get the optimal value, what we have to do? We have to do delta j by w is equal to 0. What will do? We will do like this only. Okay. So j is given. So now we'll get j by w. And we all know that y is equal to xw. So if we keep that one, delta j by delta u, so you will come half xw minus y plus half this is still j. If you take like this, it will come like what? Equal to 0. X transpose into xw minus y plus if you take like this, so it will go lambda w. And we have to make it equal to 0. So now just multiply with that xtw minus transpose actually, sorry for that, lambda w. Now do the like what you can say grouping. Grouping will do x transpose xw minus lambda I, not lambda I, plus lambda I, plus lambda I minus x transpose y. So now to get the w, x transpose xw plus lambda I inverse x transpose y. Not this will be C is the answer. Is it? Now what we have, we might going to resort the numerical that the methods such as finite difference or automatic differentiation to calculate the gradient descent instead of mathematical one. They are saying we can go for the numerical methods also, maybe the finite difference or the automatic differences and all to calculate the gradient descent. Why we are going for the analytical method? Can anyone tell why we are going for that? Anyone please tell why we are going? Because a gradient descent doesn't have the actual expression that can be of anything. But for FEM or automatic that things that will be going to require. So we don't have the explicit expression for the gradient or function is available for the only as a block box. So that's how the things will go. Analytical gradients are always expensive. No, it can be. It can be. It depends about the our problem. That things that is not going to stop us because even we have the highly computational methods are there. The function for which the we calculate the gradient is too simple, making analytical method less challenging. No, sometimes the very simple problem, sometimes the very complex problems. It can't be. Numerical method provide the more accurate result than analytical methods. No, it can't. Like it not always going to be necessary. It will going to cause the burden also. So it can't be. So third is the option. So we can see that answer that I'll keep in the drive that you can go and just read out. Now the things are there. They are saying we have some questions are there. Shall we stop for like today, or we'll solve some problem? We have to get the SSR, like it's a regression problem. Can anyone tell like I'll tell some theories we have found that now what is there? They have said the X is given and temperature we got. Okay. But there they have given the X value, like M value, and then corresponding output is given, and they are saying T is equal to just 1 minute. Okay, so they have given the T. And initial 0 W0 they have given 99.57, W1 they have given 79.28 they have given. So the thing is that now to get the SR, what is that exactly? SR is actually a sum of the square of the error, one summation of. Okay, so this is the formula for that SR. It's actually SSE. Okay, So in that case, now for x is equal to minus 0.5, we'll get p. How much? 99.58 plus W179.28 into 0.5 minus. If you calculate the value, we'll get, I have the value actually, 59.93. For x is equal to minus 0.4, t is equal to 99.58 plus 79.28.4, we'll get how much? 67.588. For x is equal to 0.3, and so we'll get 99.58 plus 79.28.3. We got how much? 59, 67, 75, 70. Then 4 x is equal to 0.0. If we keep, so it came around, that multiplication, so it came around 83.714. We'll take one page actually. Okay, so now we'll calculate the what? S E, like maybe the SSR. If something will be there. We know the formula. Uh, we know the formula is the yi minus summation. So yi, how much was there actually? That, so that we have calculated. It was the first case 48, 70, 83, 90. 48 minus how much we got? 59.93 for the first case. Second case, what we got? 70 minus 67.858. 70 minus 67.858. Third one, what we have? 83 minus 75.786. 83, 75.786. Then what we have? 90 minus 83.714 minus 714. If we calculate all this, what will get the value? 58, 49, 11, 11, 11, 121. So it came somewhere 142.33. Then 4.59, 52.04 plus 39.51. So total value came 238.5. So the answer is 238.5. Okay, it's clear now. Now the same question they are saying. Now, so that the same question they are saying to find out the ST. ST is nothing but the SST. SST, what is the formula which will be there? Summation of yi minus y bar whole square. Now the task is to find out the y bar. Y bar will be 48 plus 70 plus 83 plus 90 by 4. So if we done with that, we got 72.75. So now to calculate the ST, what will be there? Yi, how much? 48. ST, 48 minus 48 minus 72 point. Just 1 minute. So 1 minute. Hello. आ रहे बस 2 मिनट. I think my audio is not disturbed. Okay, so now we'll calculate the similarly for 70 minus 72.75 whole square plus 83 minus 72.75 whole square plus 19 minus 72.75 whole square. So if we calculate all these things, so we'll get 10 to 7.5. So this is the answer. So I think it's clear about this. Now what we have the fifth question what we have. So R square. R square that we all know that SSC by SST. So SSC what we got or SSR what we got here 238.5 238.5 and SST what we got 1020.75 1020.75. So that R square will become 1 minus 238.5 1020.25. So if you calculate the 1 minus 1 minus 0.02332, it came 77. So this is the answer. So that's all for today. We'll see the next class. Is it clear? Okay. 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 Thank you. Thank you for joining. We'll see in the next class the next topic.